Okay, are you able to see the screen?
Yes, sir.
Okay, all right. So we started with trampers, right? So last class, that was on Friday, we discussed about few prerequisites of clampers. Okay, so clampers are basically um, wave shaping circuits in the sense it shifts an incoming signal to a desired DC level. Okay, so it can shift an incoming AC signal to a positive DC level or to a negative DC level. Okay, that's the reason clampers are also called as wave shifters, or it can also be called as DC restorer. Okay, it is a DC restoring circuit. All right, fine. And for successful clamping operation, okay, what is that we should need? We need a high time constant. High time constant, that is tau is equal to RC, should be very high. Should be very high. This is very, very important. Okay, once the time constant is maintained, very high, the capacitor doesn't discharge. Doesn't discharge under any circumstance. Okay, this is very, very important. Hence, in clamper circuit, the capacitor circuit is designed in such a way that the capacitor can be treated as a battery. All right. So this capacitor C can be treated as a battery E. Okay. So the battery is going to retain its charge. Fine. So that is about the clamper fundamentals. Okay. So today let us look at the practical clamper circuits. Okay. So first let us consider ideal negative clamp. Okay, ideal negative clamper. Okay, so this is the simplest circuit amongst all. All right. Now the circuit looks like this. Okay, and this is the circuit diagram. Okay, the circuit is made up of only three elements: resistor, capacitor, and diode. All right. So this is your capacitor. Okay, connected to a diode. So for negative clamper, the diode placement is something like this. Okay, and then the load resistor. Okay. And then this combination is connected to an alternating source. Let's say we have connected the combination to a sinusoidal alternating source with a maximum value of Vm volts. Okay, so this is your C and this is your RL and this is your diode D, which is ideal in nature. Okay, so here you can write here the time constant tau is, what is it? It is load resistance RL into C, okay, which is very high, okay. And before jumping into the analysis part, okay, we are assuming that C is initially uncharged. C is initially uncharged. Okay, that means to say VC, that is voltage across the capacitor, is 0 initially. So it's a fresh capacitor, all right. So this is where you are interested in finding out your output voltage. Fine. So the circuit is ready, the assumptions are in place. Now we are good to go for the analysis part. All right. So let's write down the analysis. Okay. So C is initially uncharged, and the time constant of the circuit is very, very large. All right. So analysis. Now the analysis is broken into two parts. Okay. So in the analysis, firstly you need to find out the charging voltage on the capacitor. So you should write charging cycle. First is the charging cycle. Once the capacitor is charged, then you can go for the output cycle. Output cycle. So in the output cycle, what we do, we analyze the circuit for let's say positive half of this input, positive half of input, and the negative half of the input. Negative half of the input. So this is what is called as the algorithm for clamper. All right. So this is the algorithm for clampers. Okay. So basically, you can analyze using a three-step approach. Okay. First step, find the charging. Okay, charge on the capacitor. In the second step, probably you can find out the output voltage for a positive half cycle of the input and for a negative half cycle of the input. All right. So first, let us write down the charging cycle. Charging cycle. Okay. Now, why charging cycle is required? That's because we have availed a fresh capacitor. So the voltage across the capacitor is 0 volt initially. So we must know, the capacitor is charged to what voltage. All right. So can anyone identify the charging cycle? So in which cycle the capacitor is going to get charged? In the very first step. Okay. In the very first half cycle, the capacitor is going to get charged. Now the question is, which cycle? The positive cycle makes the capacitor to charge, or the negative cycle, half cycle, makes the capacitor to charge? Can anyone type the answer in the chat box? Can you try? Which half cycle makes the capacitor to charge? Okay, positive. That's correct, positive. So this is how we distinguish clamper. Okay. In a negative clamper, the first charging cycle is the positive half of the input. All right. So those who have told the positive half cycle, their answer is correct. Okay. So for a negative clamper, the first charging cycle is positive half cycle of the input. Okay. So similarly, for a negative, for a positive clamper, it is going to be the negative half of the input. Okay. So first is the identification of charging cycle. Done. Okay. So the capacitor gets charged during the very first negative half cycle of the input. Okay, negative half cycle of the input. So let us draw the equivalent circuit for the same. Okay, this is your capacitor. This is your diode. This is your load resistor RL. Okay. Okay. So negative half cycle. Hence, let me write down the reversed polarity for the input. Okay. So this is your input. Okay. Now, when your input is, increasing in negative direction, what happens to the capacitor charging? Okay, so the plate, the plate which is closer to the negative terminal of the source attains negative polarity. That's how the capacitor charges, right? And the opposite plate attains positive polarity. So this is how the capacitor is going to attain the polarities. Okay, once the capacitor gets this polarity, the polarity is not going to change. That's because I have already told in the beginning that we set the time constant of the circuit so high that once the capacitor is charged, it is going to behave like a battery. Okay, so once the capacitor attains this polarity, throughout the clamper operation, the polarities of the capacitor is not going to change. All right, fine. I'm so sorry. Positive half second, right? I should have changed. Okay. Positive half cycle now, because we were talking about the negative clamper. Okay. As you have told, the negative clamper charges in the positive half cycle. Okay. Positive half cycle of the input. Okay. So this is plus and the opposite side is minus. All right. So this is VC, the capacitor voltage. Okay. So as you can clearly observe that the current is flowing in clockwise direction because of the positive half cycle. So the diode gets forward biased. So diode is forward biased. FB. FB stands for forward biased. Okay, so when the diode gets forward biased, what we can do, we can replace the diode with a short circuit equivalent. Short circuit equivalent. Okay, so during the very first positive half cycle of the input, what is the output voltage? Can anyone type the output voltage? Output voltage is nothing but voltage measured across the load resistor RL. So what do you have? What element is being connected across RL? Across RL, what you have is a short circuit path. So output voltage is 0 volt for the very first positive half cycle. Okay. Very first positive half cycle. That is because across RL you have a short circuit, and in a short circuit scenario, voltage is 0. Okay. Then you apply KVL in clockwise direction. Okay. So when you apply KVL in clockwise direction, what do you get? Negative to positive VI, positive to negative minus VC. Okay, and anyhow you know that voltage across RL is 0, so that is equal to 0 volts. Okay, or VC is equal to VI. Vc is equal to Vi. Okay. So therefore, when the input attains the maximum value, the capacitor gets charged to a maximum voltage of Vm. Okay. So maximum value of positive half cycle. Okay. So the capacitor attains what voltage? Vm volts. So once the capacitor is charged, the capacitor is going to retain a voltage of Vm volts. Okay. So this is your charging cycle. Okay. Now let us go to output cycle. Output cycle. Okay, so output cycle, that means to say output voltage waveform, can be found for a set of positive half cycle and for a negative half cycle. So first let us consider positive half cycle. Okay. All right, let me redraw the circuit. Now here comes the interesting fact. Over here, your participation is very, very important. It's a diode, okay, which is ideal in nature. And then comes the load resistor. Okay, so positive half cycle, let us put the polarity, positive polarity, okay. And this is your diode. Okay. Now, what I will do at the capacitor terminal, let me just mark two nodes, node A and node B. Okay, now what you have to do is you have to tell me the polarity of A and polarity of B. Quickly type your answer. What should be the polarity of node A and what should be the polarity of node B? Please type the answer. Remember one thing I've told in the beginning, in case of clamper circuit, once the capacitor is charged, it is going to retain its charge throughout the clamper operation. Okay. Retention of charge in the sense you have to treat it as a battery. Okay. Taking that into consideration, you tell me what should be the polarity of terminal A and what should be the polarity of terminal B. Can you type your answers? Okay, perfect. So terminal A should have positive polarity and terminal B should have negative polarity. Okay, on what basis you said? The base was your charging cycle. So this is how the capacitor was charged and this is how the capacitor is going to retain its charge. So this side is positive and this side is negative. Okay, so what you have to do is you have to just treat this capacitor as a DC voltage source. Okay, so and what is a capacitor voltage? The capacitor voltage is Vm volts. That's all you have to write. Okay, Vm volts. Okay. Now you tell me in the output cycle, what happens to the diode conduction? What happens to diode conduction? Can you tell me? Will it be forward biased or will it be reverse biased? The diode will be reverse biased. Okay, let me tell you how. Okay, now if you look at the two sources, how these two sources are connected to each other in an opposing manner, right? So Vi is trying to circulate the current in clockwise direction. On the other hand, the capacitor, okay, which is behaving like a battery, is trying to circulate the current in anti-clockwise direction. Okay, so if your input is less than Vm, okay, So Vm is nothing but Vc. All right. So if your input is less than Vm, what happens? The negative terminal of the capacitor is connected to anode of the diode, right? So D is reverse biased. Okay. On the other hand, if your input, okay, is equal to Vm, okay, when your input is equal to Vm, what happens? Net voltage becomes zero. Okay. So then also D is reverse biased. Okay. So this is the very important observation in clamper. Once the capacitor is fully charged, what happens is that in the output cycle, the diode D remains off. Okay. Now, I have taken only two cases. Input can be less than the capacitor voltage, or at the maximum, input can be equal to the capacitor voltage. Can you have this condition? Can you have a condition wherein input can be greater than Vm? Yes or no? Type in your chat box. Can my input, okay, attain a value which is greater than Vm? Is it possible? No. Why? That's because Vm is the maximum value of the input. So at the maximum, your Vi can be equal to the capacitor voltage. Okay, so you can get only two conditions. Either input is less than Vm, or the equilibrium condition wherein input voltage and the capacitor voltage becomes equal. So when the two voltages are equal, what happens? The net voltage becomes zero and diode is reverse bias. So you can write that something like, for the entire positive half cycle, diode is reverse biased. Okay, if the diode gets reverse biased, and this is how the circuit is going to look like. Okay, the capacitor, and there's an open circuit here because diode is replaced with open circuit equivalent. That's your load resistor, and this is how you will observe your minus plus. Okay, so this is your Vi and this is your Vm. Okay, let's apply KVL. Okay, so apply KVL in clockwise direction. Okay, so when you apply KVL in clockwise direction, what do you get? The KVL equation as Vi minus Vm minus V0 is equal to 0, or output voltage V0 is equal to Vi minus Vm. Okay. So what we can do, we can just make a small table. This is my Vi and this is my V0. Okay. So when your input is 0, okay. So when your input is 0, what is your output? Output is minus Vm. So let us write minus Vm. And when your input attains positive maximum, that is plus Vm volts, what happens to output? Output becomes Vm minus Vm, or Vm is equal to 0. So when your input attains positive maximum, output becomes 0. Okay, so this is for positive half. Okay. And then you are supposed to predict the output for negative half cycle. Okay. Is it clear, the positive half cycle analysis?
Yes, sir.
All right. So now let us look at the negative half cycle. Okay. Okay, the same circuit, the diode and the load resistor connected to input source. Okay. Now here the input polarities are reversed. Okay, because we are dealing with negative half cycle. Okay, what about the capacitor terminals? Capacitor is, given with the same polarities. Okay, so this is your VM. You are not supposed to change the capacitor terminals. Okay, that's the rule in clamper. This is how you are going to observe your output. Okay. Now you see in negative half cycle, what is happening in the negative half cycle? In the negative half cycle, it is clearly visible that both the sources, Vi and Vm, are trying to circulate the current in anti-clockwise direction and thereby reverse biasing the diode. Okay, so this is how the capacitor is trying to circulate the current, and this is how the source is trying to circulate the current. Okay, so both are trying to circulate the current in the anti-clockwise direction, and therefore diode stays off for the entire negative half cycle. Okay. Now it is very clear that whenever we were trying to find out the output voltage in the positive half, the diode was non-conducting, and in the negative half also the diode was non-conducting. So you can trust my word, for output cycle your diode stays off, either it is positive half cycle or negative half cycle, and this is true for positive clamper as well as negative clamper. Okay, so this particular observation will greatly help you in quickly solving the clamper problem. Always open circuit the diode circuit during the output cycle. Okay, so the diode gets open circuited. So when the diode gets open circuited, the equivalent circuit takes the following shape: plus minus, this is Vm, this is Vi. Okay. Open circuit the diode and retain the load resistor part, and this is your V0. Right, this is minus and plus. Now what you do, you apply the KVL in the anti-clockwise direction. Apply KVL in ACW, anti-clockwise direction. So what do you get? Negative to plus Vi, then minus to plus V0, then minus to plus Vm. Okay. So basically you get additive polarities of three sources: minus to plus, and minus to plus, or V0 is equal to minus Vi and minus Vm. Okay, minus Vi and minus Vm. Okay, so this negative sign, okay, indicates that, okay, phase reversal. That means to say the signal has changed its direction. Okay, so now let us see what happens to the output during the negative half cycle. Okay, so when the input is 0, okay, for the negative half cycle, when Vi value is 0, okay, V0 becomes 0 minus Vm, that is minus Vm. Okay. On the other hand, when Vi becomes Vm, okay, in the negative direction, your output becomes minus Vm, that is equal to minus 2 Vm. Okay. When your input is 0, output is minus Vm. And when your input is Vm in the negative direction, okay, negative half, negative peak it is, okay. So your output becomes minus 2Vm. Okay, so what I will do, I will substitute this result in this table. So when your input is 0, output is minus Vm. And when your input is hitting the negative maximum, your output stays at minus 2Vm. Okay. So let us sketch the waveform. Okay. So first let us draw the input. Okay, so this is our input. Okay, t omega t doesn't matter. Okay, and then you draw the transition points. Okay. And now let us draw the output. Okay. Now you tell me, when your input is 0, what was the value of the output? For 0 input, output voltage was minus Vm. Minus Vm. Correct. In the positive half cycle. In the first positive half cycle, we have seen that when your, in the output cycle, when your input is 0, output is minus Vm. And when your input attains positive maximum, when your input attains positive maximum, your output attains 0 voltage. Okay. Similarly, when your input becomes 0 volt, the output stays at minus Vm volts. Okay, so this is how the output voltage okay, so that's your output. Similarly, in the negative half cycle, okay, in the negative half cycle, this is the negative peak, okay, the negative half cycle. When the input is 0, output once again becomes minus Vm. Okay, so it's right here. And when the input becomes, Vm in the negative direction, the output becomes minus 2 Vm. So this is minus 2 Vm. Okay. Once again, when the input becomes 0, the output stays at minus Vm volts level. Okay, so this is your output. Okay. Now, what observation you have to do over here? So your output is being shifted by how many volts? Shift is equal to dash volts. Can you type in your chat box? What is the shift that you are observing in your output waveform? What is this shift? Vm? DC is a polarized supply, right? Whenever you say Vm, you should tell me whether it is plus Vm or minus Vm, because that's how the clampers are identified, right? Clamper circuit either shifts your waveform, an input waveform, to the positive side or to the negative side, right? It is minus Vm. So the shift observed over here is minus Vm. Okay. Since there is negative sign, that's the reason it is called as negative clamper. Okay. So here you can write the waveform, the input waveform is shifted down by an amount of minus Vm volts. Okay. Since the shifting is taking place in the below the reference value, it is a negative clamper. Okay. Since the shift is negative, the clamper is called as a negative clamper. A negative clamper. It's a negative clamper. All right, so that's the working of a clamper circuit. Okay. All right. Any doubts in this? Any doubts in this? You can ask me.